Hello everyone, welcome to my new video on the second fundamental theorem for vector line integrals. And today we're going to talk about this fundamental theorem that's not really mentioned in the calculus textbooks and bring light to it. So let's get started. So first off, let's do a small review. And that is, we are already aware that there's a tangential line integral where if I have a curve C, typically going counterclockwise, and if there's an endpoint A and B like this, right? And if there's a vector field F, and I take it and I integrate this dot product over the domain C, then we get an answer. But if F is conservative, such that F is equal to the gradient of F, and the curl of F is 0 vector, and of course, if F is well defined, then we reach the fundamental theorem for conservative vector fields, or I'll call it the first fundamental theorem, and that is it yields the value of F at B minus the value of F at A, showing us that the value of F only depends on the endpoint and nothing in between, which is kind of nice. All right. So that's the first fundamental theorem, and this is definitely well covered in many textbooks. However, we don't really know what's the fundamental theorem for vector line integrals of the normal component, which is usually f dot n ds. There's no theorem that's given to us. And so we would like to derive it and show you that there is actually a second fundamental theorem. All right, so let's get started. So first, we create a restriction that f is a 2D vector. And this is because if f is a 3D, then the problem with it is that n is not orientable in the sense that there are infinite directions that n could go, but we only want to make sure that there's only two possible orientations. Right? And of course, there's other conditions that we need, but we don't know yet, so we're gonna add to this list a bit later. So for now, let's just assume that we want to find an answer similar to this in some sense. Right, so first we need to define n. N is a unit normal vector. So if I have a curve C that goes like this, then typically n will go this way because n is actually just r prime of t, but rotated pi half or 90 degrees clockwise. Alright, anyway, so if r prime of t is, then we know that n, by a linear transformation of rotate 90 degrees clockwise, will be this. Right, and if we put this back in and kind of rearrange it, then we end up getting, and of course, oh, and sorry, I should have mentioned this earlier, assume that f is components of this. And we start from time naught to time final. Then we end up getting, after evaluating the dot product, then we get f1 y prime minus f2 x prime dt. But if you rearrange this by swapping the order, then we end up getting minus f2 f1 dot product of x prime y prime dt. And this actually just ends up simplifying to be, which is actually just the tangential line integral shown in the first place. And we know how to find the fundamental theorem for this. And so let's call this vector g. And assume that g is conservative. If so, then we end up getting the gradient of g equal to this, and we know that the curl of g is 0 vector, and we know that g is well defined, which leads us to the conclusion that it is g of b minus g of a, and hence we get our second fundamental theorem of calculus. So let me restate this. So assume that these conditions are satisfied. Then there exists a fundamental theorem for a normal component vector line integral such that f dot n ds yields g of b minus g of a. And this is a fantastic result because, again, the flux line integral does not depend on the path taken, but rather only at the endpoint evaluated by the function. But now we want a more specific condition. Rather, can we evaluate whether we can use this theorem without directly consulting with G? And there is, actually. So we start with the definition that G should be conservative, which implies that the curl of G is a zero vector. And so we apply the curl of G, and we actually just end up getting df1 dx plus df2 dy of the k unit vector, and we notice that this has to be 0, which implies that the divergence, right, because this is the divergence of f, just simply needs to be 0. And of course, we need to assume that we definitely need to know that f is well defined. But once these two conditions are satisfied, we are able to use this critical fundamental theorem. So let me box this in red for clarity. And that, my friend, is the second fundamental theorem. And I will also lay the conditions that for this to work, the divergence of f must be 0 and f must be well defined. And of course, we know that that the gradient of g needs to equal minus f2 f1. All right, my friends, that's pretty much it for the theory. In my mathematics website, there is a PDF that corresponds to this topic where there are a few practical examples that show you how to actually calculate by using this theorem. And so please take a look if you're interested. All right, everyone, thank you for watching my video. Please give a like, and please subscribe. And hopefully you found this video very enjoyable, and I'll see you again sometime later. All right, my friends, bye!